Hi, I'm Dave Breckle from Omron Electronics, and today we're going to discuss the phenomenon of skin effect and its influence on cables within the control panel. You might be familiar with the principles of electromagnetism. Essentially, if you pass current through a cable, it'll generate a magnetic field. And in fact, Fleming's right and left-hand rules, which illustrate these fields in motion, govern the actual principles behind all of our motors and generators. Here we have what's called Maxwell's corkscrew rule. If you imagine that your thumb is the conductor and that the current is passing through in the direction of your thumb, it'll generate a magnetic field that you can see and be around the conductor itself. When we're dealing with high currents or high frequencies, that magnetic field has an effect back on the cable. So if we look at this diagram, if you imagine I is the current flowing through the cable, H is the magnetic field being generated that's surrounding it as per our Maxwell's rule, and IW, the red circles, are actually eddy currents that are being created in the cable by the magnetic field. These eddy currents oppose the flow of current and essentially push all the current flow to the outside or the skin of the cable. The higher the current and the higher the frequency, the more pronounced the skin effect is. Here we can see a video of an induction heater, and this is basically creating a very strong magnetic field, which is creating eddy currents in the knife, heating it up, and you can see the skin effect happening as it starts to glow around the outside. Incidentally, the induction heater itself is actually made of copper tubing. Because you're passing a high current and frequency through it, there'd be no current flow in the middle. And this is also a similar principle that you might see in a waveguides within a radar plant, for example, or a piece of equipment. So, essentially, the higher the frequency, the more pronounced the skin effect is. The other thing that can affect skin effect is actually the material the cable is made of. So in the case of copper, for example, here, at 50 Hz, i.e. what we'd have for mains, the skin effect is 9.2 millimeters. So for anything up to about an 80mm cable, you don't really have to worry at all about skin effect. At higher frequencies, such as 10 kHz, that skin effect is reduced down to essentially 652 microns. And when we start looking at very high frequencies, like 100 kHz, you may only be using 200 microns of the cable itself. Now, the reason why this is important in control panels is if you've seen some of our earlier tech talks, we speak about harmonic distortion and the high frequency noise that's generated by inverter drives. In these situations, we are talking about frequencies that can be in the 10s or above kilohertz. So, essentially, for low voltage and mains and DC, solid cables will suffice. But when we start dealing with cables that might be carrying higher frequency, whether that's intentionally or with harmonic noise, we then have to look at using stranded cable, or what we would call lights wire. Lights wire is essentially made up of a number of small cores that are wound in a specific pattern to ensure that the effects are spread across it. Also, each individual cable or strand is insulated, so you end up with skin effect across a wide number of individual cores rather than one large core, giving you a larger surface area. And this principle can actually be seen in the construction of your standard earth bonding strips that you might see within a panel. This is very important, as we mentioned, because obviously when you're looking at harmonic noise, we have to look very carefully and consider into various cable shielding and mitigation strategies, and this is what we'll be discussing in our next panel tech talk. If you'd like to know anything about Omron or any further information, you can visit our website at industrial.omron.eu, or you can contact our technical team with any queries direct on ukts@omron.com. Thanks very much.